yeah, my talk is about how Shopify scales Rails. So first up, just what is Shopify? I already had someone confuse us for Spotify, so we're not Spotify, we're Shopify, so we do hosted online e-commerce. We make it really easy for just about anyone to set up an online store and get started with that. So I grabbed a couple pictures of our office. So we're really trying to make it, we're based up in Ottawa, Canada, so we've made our office like really fun, like pulled a lot of really interesting things from different offices in Silicon Valley, and it's a really amazing, really cool place to work. So I like to share that with everyone because it's a really cool place. Even though we're up in Canada and it's like really cold all the time, this kind of makes it worthwhile. Anyways, like into the talk. So I'd like to just share like kind of our stack, what we run on. So we're running Ruby 1.9.3, patch level 3.27, Rails 3.2. We just like made the big bump from Rails 3 to Rails 3.2 Monday. So that was pretty crazy. We use a Percona flavor of MySQL 5.5. So Percona has their own builds of MySQL that we use. They add a lot of instrumentation and performance patches, so we use that. And then we're running on Unicorn, Memcache, and we have Redis in the stack. So that's kind of the main moving parts to Shopify. So it kind of looks like this, you know, Nginx and Unicorn in front of Rails and Ruby holding everything up. We have 33 app servers, 1,172 Unicorn workers, 5 job servers, and 307 job workers. So lots of stuff processing, lots of stuff happening at once, which is pretty cool. So this is kind of what a little piece of the cluster looks like. We have firewall, load balancer. We have our app servers, which are then replicated across. We have search and Redis, job servers. Pretty standard setup, and we can scale all these pieces horizontally, which is pretty great. Just an idea of the amount of code in the Shopify project itself. So we have a bunch of like projects around Shopify itself. So these stats are just for the Shopify core product itself. So 55,000 lines of application code, 80 lines of test code, 211 controllers, 468 models. So there's a lot of code in there, and there's a lot of stuff going on, lots of Ruby. So what's our current scale? Like how much are we doing? And what does that look like? So last year, we processed 9.9 million orders on behalf of our merchants. And this works out to be an order every 3.2 seconds. So that was pretty amazing last year. On Cyber Monday, we processed 2008 sales per minute. So Cyber Monday is traditionally our busiest time of year. So we were doing 2008 sales per minute, which is pretty crazy. One really amazing thing about this is in about a month or two, this is like our regular transaction rate. And next year, it'll be double. So it's really amazing just like how fast things are growing and how fast we're needing to scale and deal with this stuff. So we run at about 50,000 requests per minute on a regular day. And we keep it pretty steady at about 45 millisecond response time. So lots of requests, and we're serving them really fast to make our users happy, which is really cool. Last year, we served about 13.3 billion requests. So this is just Shopify itself and all the CDN and all the image requests. But just the core application, we served 13.3 billion requests, which is a shitload of requests. So before I get into it too much more, I really think it's important for us to look at like where we came from and like what happened in the past. I find, like myself included, our generation of developers, we really like to look at the new things, the new technologies that are coming out. But it's really important to look at what's happened in the past to get like an idea of what's been done and what's been solved and how it's been solved. So this is just a look at the history of Shopify. So the first line of code to Shopify was written in 2004 by Tobi in like a coffee shop somewhere. We released the first version in 2005. It's been the same code base since that initial line of code was written. If I tried hard enough, I could probably find those first couple of lines of code in there in the history. So that's 9 years of Rails upgrades, improvements, and changes on the same code base. I'm not 100% sure, but at this point, I'd say we're like one of the longest running Rails applications out there, seeing as the Basecamp last release, I believe they rewrote most of it. So longest running Rails app as far as I know, which is really cool. So looking back at the stats for when Shopify was released in 2005, they had 6,000 lines of code. There was a lot less test code, a lot less controllers, and a lot less models. So over this time, we've grown substantially and had to deal with all that growth. And this is what the stack probably looked like at that time. So I dug through the first couple of commits and just looking at some timelines to figure this out. But we were probably running on Ruby 1.8.2. We were for sure using a version of Rails before 1.0. We were tracking the master for a long time. We were probably on MySQL 4.1. We were using Lighty instead of Unicorn, and Memcache was already in the mix right from the get-go. Some interesting things to think about if you're a Rails developer, like I kind of went through what wasn't in Rails at this time. So like you don't have any RJS, you don't have any response to, there's no like respond with. Response to was like deprecated for respond with. There's no like nested includes for eager loading, polymorphic associations, Capistrano, REST, resources, scopes, gem files, thread safety, rack. None of these things existed when we first released Shopify. So it's really amazing, and we've come to upgrade and like depend on all these new things over time. So it's really cool looking back at where we came from. So into the meat of it, know the system. So to me, the most important part of scaling your application, you really need to know what it's about. So there isn't really any magical formula to scaling. It's knowing the characteristics of your particular system and changing or removing the constraints it imposes. And your constraints are going to be very different than the constraints we've had. Our constraints are based on an e-commerce platform where we have an admin and a storefront. The storefront is used by the customers to make purchases, and the admin is used by the administrator of the shop. The storefront is the most important part of the system because we want transactions to happen. So that's where we're going to optimize things. And knowing this is like a big part of the battle because you need to know where to start for your optimizations. If we started optimizing the admin, we'd be wasting our time because that's not the most important part of the system. So one request, one process. So we're using Unicorn, so the way we have it set up, we have one request, and it's handled by one process. This isn't necessarily true for all applications, but I believe most Rails apps are set up in this way. You might be using a threaded web server, and might not be the case, but most of us are in this situation. And knowing this fact is really important for us to know how to scale, because now we know that this is the situation we're in. We have a process, and it's handling a request. And if we want to make these faster, we add processes, or we make the individual processes themselves faster. So I mentioned our RPM, or request per minute, earlier. So this is kind of the formula for, actually this is wrong, it's not a 1, it's a 60. But it's request per minute is workers times 60 over the response time. So I was using the numbers from that I had on the previous slide, and we can calculate the potential RPM for Shopify using the number of workers and the response time that we have. So if we use that, we can come up with a potential RPM of close to 1 million. And the key here is it's a potential, because there's a lot of other factors that are involved when handling the requests. But this gives us kind of an idea of the pieces that we can move around to help to scale and help to improve how much we can process. So the two main knobs that we have to dial are increasing the number of workers or decreasing response time. So increasing the number of workers is pretty easy. We add boxes, we can add more processes. That's not a big deal. What gets tricky and where the interesting work lies is decreasing response time. And knowing that these are the things that you have to work with is really important when you're trying to scale a system. So if we want to increase response time, the things we want to do is avoid network calls during the requests. So anything that's happening during the request, we want to cut them out if possible. If we have unavoidable network calls, like calls to Memcache, call to Redis, whatever they are, we can try and speed those up in whatever ways we can by using faster libraries or dropping down to C code if we need to. In Shopify's case, the storefront and the checkout are the most important things. So these are the things that we focus on initially when trying to speed up Shopify, because these are the parts that are getting hit by the most users. And knowing that this is the most important part makes it easier to figure out what you need to do. We also have this interesting sort of aspect to our system called the Chive. Does everyone know what the Chivery is? So they're this funny website, and they sell T-shirts and stuff online. But they do flash sales. And so this is an interesting aspect to our system that has come up in the last year or so, is having to handle these flash sales. So to just give you an idea of what this looks like, this is a New Relic graph of a Chive that happened today at 11 o'clock. So the numbers are maybe a little bit blurry, but you can see the regular RPM is around 55K, and then we spike up in about 10 minutes to 200K. And then that lasts for about 10 minutes and then drops down. So knowing the fact that we have to handle this, we can't just deal with scaling at the 50 or 75K RPM. We need to be able to absorb these huge spikes in traffic, which makes it really tricky, and we have to have all this headroom to be able to absorb these things. And sometimes they're nice enough to let us know when these flash sales are happening. A lot of the time we don't know. And as we add more customers doing these things, because flash sales are really popular, it's hard to predict when these are going to happen. So we just need to be able to handle these sort of spikes in our system. So one of the big things is just measuring everything you can get your hands on. So knowing how fast things are moving within the system and looking at the parts that are most important and measuring those things is really important. So we use a few tools. New Relic, a lot of people have mentioned it. I think most people use New Relic. It's one of the most amazing tools to be able to get insight into what's happening with your application. We also use a tool called Splunk, which is a log analyzer. So we throw all our log files at Splunk, and it lets us query them, build graphs and reports, and give us a lot of historical insight into what our system's doing. And that's really amazing. We use StatsD in a very similar manner, so we are able to record different statistics that New Relic can't give us. And Cacti is similar, but for MySQL. So we use that to record historical statistics and generate graphs and be able to see what's been going on in the past and how we've been changing the system and how that's been improving or degrading performance over time. We've also developed this tool in-house called Conan, and we use this to actually test the production system under load. So Conan is a tool that's been developed. It's still internal, but at some point we'd like to open source it. But it lets us throw huge amounts of traffic in somewhat realistic traffic patterns at the production system. So we've segregated an app server, and we're able to pull it out of the main rotation. And we can point particular shops at the app server, and then we can use Conan to drive traffic to that app server. And this way we can test the changes and see how they perform under load, collect data, and see where our bottlenecks are. So it's a really great tool, and it's really important to test your system, your production system, under load to see how it's going to behave, because you're never going to get the same sort of statistics when running in dev. So just to show you some of the information we get from New Relic, I think most people use New Relic, so it gives you like an idea of the web traffic, memcache, database, Ruby, and where all the time's spent, and you get to see your throughput over time. This is just a little example of what we get from Splunk. So this is, it's not very clear, but this is a graph showing HTTP response codes over time. So with this, we're able to set up alerts. So if 500 codes start to spike, this is a good indicator that something's wrong. So as long as it's all like 200, 300s, everything's good. But Splunk gives us this real-time sort of log analysis to be able to see what's going on right now, and we can react to those, whatever's happening. We've also started putting stats in front of the team. So we've built these dashboards. We have an open source framework called Dashing that lets you build these really great dashboards with information. So we have them spread all over the office and put them in front of the teams. And these are really great motivators to tell people where we need to focus our efforts and what needs to be improved. So we've spent a lot of time on Shopify core and the storefront. So we've got like requests down to 51 milliseconds, which is amazing. But as you can see, the Shopify API, 300 milliseconds is kind of terrible. So that's where we need to like be focusing our efforts now. And knowing where you need to focus the effort is like half the battle. Another really interesting thing we did is we literally printed out everything from storefront requests on paper, and all the database calls, all the memcache hits, everything that was happening. So we did this before Cyber Monday this year, where we were doing a big performance push. And this was really great, like just putting a real enemy in front of the team so that we had something to attack. So we could go up and literally like cross things off as we fix them, and just basically go through and slash all the requests down and cut out whatever we could. So putting information in front of the team is super important. So now that we're measuring things, now that we know what we need to do, what are some things that we can do to improve the performance and help us scale? So caching is one of the big things. So we have a gem called Cacheable. So this is controller-based page caching, and it's memcache backed. So it's up on a public repo so people can use it, which is pretty cool. One of the neat things with it is we serve up the gzipped content to the browser if it supports it, and we also store the content gzipped into memcache. So storing it in memcache gzipped is really handy because it'll increase the response time when talking to memcache, and then serving up the content gzipped when we can just cuts down the amount of work we need to do, so we don't need to deflate it every time. So one of the interesting things with Cacheable is it uses this idea of generalizational caching. So this means each cache key is a generation, and it changes over time when the data changes. So in Rails, this is as simple as using like an updated at timestamp. So when the data changes, the cache key changes, and you'll get a cache miss and load the new data and push it into memcache. When the next request comes in, if nothing has updated it, you'll get a cache hit and serve it from the cache. And this doesn't have an explicit expiry on the cache. So the cache keys changes, and the data just falls off the end of the cache as it isn't used anymore. So this is a little bit of code showing how you can use Cacheable in your application. So this is just your controller, and you have a response cache block, and you just define what the key is based on. So in Shopify, we actually have a version on our shop, since everything's kind of keyed off the shop. When things change, we increment the version of the shop, and that busts the cache for us. And then there's another piece to it, which includes a middleware. So if there is a cache hit, it won't even hit the controller stack. So it's nice and fast. It'll serve it out of memcache really quickly, which is great. So another thing we started doing recently with Cacheable is started caching 404s. So errors are like unexpected, and 404s happen. And it's not really the first thing you think of to speed up. But when people are typing things in randomly or trying URLs randomly, we get a lot of 404s on Shopify. So caching those 404 pages actually was pretty huge for us. So you can see the red line is the cache misses, and you can see when we started caching 404s, that dropped drastically, and we had a lot more cache hits, which is the blue line. So we saw a lot of performance improvements once we started doing this. And just looking at our traffic patterns, we were able to determine that we were having a lot of 404s, and this was a pretty easy win to add some caching to. So another really interesting tool that we built in-house is identity cache. So this is actually really similar to that, what Brian was talking about, record cache or something like that. So this is a Memcache-backed model caching. And this was written a few years ago by Tobi and kind of went unnoticed in Shopify for a while. And then as we were really trying to improve performance, we've started using identity cache all over the place to cache as many models as we can in Memcache so we don't need to hit the database as often. So this lets us cache full model objects in Memcache. We can include associated objects in the cache. We can embed them with the parent object, so you can load the parent object and you get all the associated objects back, which is really great. We made this an opt-in caching strategy, so you need to say which models and which associations need to be cached, and you also need to opt into using the cache because there's certain points when you want the fresh data and certain points when you can live with cached data. This also has explicit expiry, but we've made it automatic by hooking into after commits, so you don't need to worry about it itself. This is still internal as well, but I've been working the last couple days on extracting it out as a gem, so hopefully people can start using it themselves soon. So a little bit of code showing how you can use it. You just need to include identity cache, and then you specify the index for the model itself. And then you can say that it's caching the associations, and the embed true tells it we want to embed the associated images with the product itself. And then it just adds a couple methods to the product so that you can fetch it by the shop ID and ID. And then when you get that product out of the cache, it already includes the images. So you can call fetch images, and you won't hit Memcache, and you won't hit the DB either. It'll already be there for you. So this is just an example of where we added identity cache to one of our models. So we can see that the average call time is really high and throughput is really high. And then at that particular point is when we deployed the change to identity cache links. And there was a huge drop because we're now serving most of them out of the cache and not having to hit the database for them. So we've had a lot of really big wins by adding identity cache and storing more things into Memcache, which is really great. So get into my process. The easiest way to speed up a process is to just kick things out of it. So you can speed up what's in there, or you can just throw it right out of the process so the process doesn't need to do the work, and it can move on and do other things. So one of the ways to do this, delayed job. So this is something Tobi wrote back in 2010 or 2009. And so delayed jobs is just a job server, and you store the jobs in the DB. You run another worker that pulls the DB and processes the job. It's pretty straightforward, pretty easy to use. It's on GitHub. Collective Idea has been maintaining it lately. So that's what we started with back in 2010, 2009 when it was introduced. We moved to Resque, which is Redis backed. So the big reason to move to Resque was we no longer had as much DB contention. So if you go back to one of my earlier slides, I said we have about 300 job workers. So if all those job workers are hitting the jobs table, polling constantly, we're going to have a lot of contention on that table. and it was causing trouble as we wanted to grow the number of job servers and workers because we have a lot of jobs to work off. So just removing that bottleneck and moving things to Redis helped us a lot, so we no longer had the DB contention. There's also a fact with Shopify that we just do a lot of writes to the database. A lot of things change often as things are being purchased, as products are being added, as orders are being created, so we need to write all that to the database. So whatever we can do to offload things from the database is going to be a big win. It's also faster because Redis is really good at just pushing data into it. So we're able to do 300 jobs per second versus 120 jobs per second. And there's also some nice extensions that we've been able to take use of, such as exponential backoff, some locking plugins, and status plugins, which just make using jobs a lot more easier and a lot more flexible. So what we use Resque for, these are some of the types of jobs that we have for Resque. So we send emails, we process payments, we do geolocation, import-export for our indexing on search, and I went through and grepped for all the jobs, and there's 86 other ones. So we use jobs for just about everything we can, so we can offload the work out of the main process that's handling the requests for the user. So just an example of some of the improvements we saw. So this is what we saw when we started backgrounding payments. So one of the things with processing payments is majority of the time it's handled by HTTP calls. And the payment processors, they're usually backed by banks, which aren't very fast. And so there's a lot of fluctuation in the response times. And it can be very slow. So moving these into a background job cut the response times in half, which was really great. And it also normalized the data a little bit, or the response time a little bit. So we had more regular traffic patterns because we weren't getting as many variations in the requests to the payment gateways. So just a little example of how you can use Resque. It's pretty straightforward. I think most people know how Resque works. You just define a job, and then you can push that job with the data it needs onto the queue. You have workers running, and one of the workers will pick up the job, initialize the class, and pass the parameters, and work it off. Really straightforward, really easy to add to your app to help you scale things up. One added benefit to adding Resque is we now have Redis available to us. So initially, we just had Redis for Resque, but we've started using it for a lot more things. So one of the big things is the inventory reservation system. So we use Redis and the Lua scripting available to make really fast reservations on inventory, which is really important during the checkout process and one of the most heavily hit things during a flash sale. We also store our sessions, theme uploads, we do some API throttling, and we use it for this thing called sequence columns, so we can just increment columns scoped to a particular store. So this used to be database backed, and again, we ripped it out of the database and started using Redis for it because Redis is really good for these types of incrementers. So in Shopify's case, all roads lead to MySQL at some point. At some point, we're going to be writing data to MySQL. So whatever we can do to speed up MySQL and speed up how it can handle the requests is going to be a big win. So the type of hardware we run our MySQL servers on, they have a lot of cores, they're filled with SSDs, we have a lot of RAM, and this allows us to keep the full working set in memory. So our DB is about 450 gigs, and with 256 gigs of RAM, we're able to keep the main working set into memory. And keeping it in memory, we were able to see about a 10 to 15 times improvement in speed because it doesn't need to read from the disks, and there's no I/O holding it back. So if you can, it's really great to keep all your working set in memory if possible. And RAM's cheap, so it's easy to do. So we also started doing a whole bunch of query optimization. So we use PT Query Digest, which is a Percona tool So we use the Percona version of MySQL, so they add a lot of instrumentation, add a lot of tooling. And this is one of the tools you have available to you to look at the queries and see how they're performing and try and optimize them. One important thing is to avoid queries that generate temp tables. So this happens really easily with group bys and order bys that use different columns. And if you have most of your working set in memory and you do this on very large tables, you can very easily start writing to disk, which will lose all those benefits of keeping the working set in memory. So you really want to avoid that. We also just really focus on adding the right indexes and forcing and ignoring indexes in some cases. So in Shopify's case, the orders table is kind of the key to most of the system. So it's used in a lot of different places, and we have a lot of indexes on it. And this means MySQL sometimes can make the wrong decision about which index to use. So we need to coax it and tell it which indexes to use in some cases, and in some cases tell it to ignore indexes so it'll do the right thing. We also did a lot of MySQL tuning recently. So I picked out a few of the sort of variables that we tuned recently that were kind of interesting. So one of them was the InnoDB stats on metadata. So in a Rails app, a lot of times when it's requesting data, it's going to do an explain on the tables to see which columns are there. So this explain does a bunch of extra stats and a bunch of other sampling of data most of the time, which is just extra work that we don't need to do. So by disabling this, we were able to cut out that work that it's doing and make MySQL respond that much faster. We also increased the table open cache. So since we have a lot of CPUs, we're able to have a lot of threads running, and increasing the number of tables open lets those threads work harder. One key when you're starting to increase connections or table open caches, you really need to make sure they're in sync. So if you increase the number of connections and don't increase the number of table open caches, or don't increase the file descriptors, you're going to run into those limits instead. So you really need to watch out what you're increasing and making sure they're all in sync when they're related to each other. Another thing we did was replace the glib memory allocator with tcmalloc. So MySQL has about a half dozen different memory allocators you can use with various performance indicators. So in Shopify's case, since we're very write heavy and we have a lot of threads interacting with the database, we found that tcmalloc gave us a good amount of performance increase, so we switched to that. But you should really look at your own system and see which memory allocators make sense for you. Another thing we changed was the InnoDB auto-increment lock mode. So this is really important for tables that have auto-increment columns, which most Rails apps do. You have the auto-increment primary key. So what this does is, so it optimizes inserts into tables with auto-increment and makes it more scalable and performant on those types of tables. The drawback is it may degrade performance when using it with bulk inserts. So this isn't really something that we need to deal with. So we made this switch to optimize for the regular inserts into these tables. So another interesting thing with the DB and Rails in particular is after commit hooks. So these are really cool because it gives up the transaction and lets it work on something else. Because you don't want to hold the transaction open for too long because you have a limited number of undo slots in the database, which are held open per transaction. So if you can give up the transaction and let something else do work and do your work in another transaction after commit, you're able to speed up the overall request. So the way after commit works is it fires after the transaction has been committed. Another added benefit is you know the data is in the database, which is really great. So we use this for our webhooks, which we fire to API clients. So this way we know the data has actually been persisted. We were running into issues with stale data, and having these happen in after commit meant that the data was in the database and it was we knew it was there, so that's really good. Cache expiry, so this is a great place to expire your caches because you know the data's been persisted, you know what's there. And it's also a good place to update associated objects. So when we have orders created, we want to update our customer objects with the totals that they've spent. So we do that in after commit, so we can commit the order transaction. And then we just create a new transaction for the customer, and we can commit that on its own as well. So a little code sample of after commit. One key thing with after commit is the object you're given has the changes blown away already because it's been committed to the database. It's already been persisted. So we often use after commit hand in hand with after save. So we'll check the changes and see if we need to do some work. We can set a flag, and then in after commit, we can check that flag and do the work that we need to do. So again, it's pretty easy to use, but just the fact that you're dealing with multiple transactions makes it a little bit more confusing, but well worth the effort. So another point I wanted to touch on is services. So I found Brian gave a really great talk on services, and I can't really add much more to what he was saying. Adam and Brian both, they talked about not pulling out services until you really need to. I can't reiterate that enough. You really don't want to extract services when you don't need to, because it does make your system more complex. So you want to wait and split them out as standalone services as it becomes necessary. One of the big benefits is that they can be independently scaled. One of the things that was talked about a lot is just how do you know what and when to split out services. So one of the things that I was kind of thinking about after Brian's talk was when you have to start segmenting your metrics to get any meaning out of it, that might be a good indicator that you need to split out a service. So I'm just going to talk about one of the services we split out, which is called Imagery. So Imagery handles dynamic resizing of images. And so what we were seeing is we used to have Shopify, the application, serving all the images and dynamically resizing them. At some point, it became obvious that those requests were kind of overshadowing the other application requests. So it was hard to actually determine much meaning from the overall data that we were seeing. So that was a good indicator that it was time to move Imagery out onto its own service. Handling image processing is also a pretty good sort of standalone thing that we can do. So we split it out onto its own service, and we can scale it independently and deal with any sort of scaling issues on its own. So the way Imagery kind of talks to Shopify is Shopify will push the assets into S3, and all the image requests will go through the CDN and hit the Amazon ELBs, which take that HTTP traffic to the front-end instances, which are made up of some HTA proxy and varnish caches. So these machines are really, really RAM heavy because they're big caches. And so if there's no cache hits, it'll send the request to Imagery, and Imagery will do the processing of the images and send it back through the stack, and it'll be cached. So one really great thing with this architecture is, for one, we're able to scale Imagery servers on their own. They're all in the cloud, so we're able to increase and decrease them on their own, which is really great because storefront requests happen kind of sporadically. And we don't know exactly when a whole bunch of image requests are going to be coming in. Another good thing is by splitting up the front-end instances and the back-end instances, we can optimize the hardware for the specific jobs they're doing. So those front-end instances are really RAM heavy because they're big caches, and the back-end instances are CPU heavy because they're doing image processing. And so we can scale each of these horizontally as needed, which is really great. And I find this is a really good definition of a service because it stands on its own. There's very limited points of interaction, and you want to be able to scale it independently. So if you have things like that in your system, they're probably good things to split out. But you really want to watch out and not split out things unnecessarily because you're going to increase the overall complexity of your system, and it'll be harder to maintain and harder to understand. So kind of the key things that I was hoping you would get from this is just to adapt and evolve as needed, and to use the data and knowledge of the system to drive your decisions. So everything we've done in Shopify, we've done as the data's dictated, as things have changed, as we've grown. We've never prematurely optimized anything. It's as it becomes necessary, as it becomes apparent that things should stand on their own, that's what we do. So hopefully that's will help you with scaling your own applications.